Welcome to lesson 6, example number 1, and it is asking, or is saying, that the stem of a cantilever retaining wall is 12 foot high, so I'm going to go ahead and draw this. This is what I'm assuming it looks like. And it may have a key, it may not. But here's your stem. That's what they call the stem. This is the toe and the heel. And it says it's 12 foot high. Sorry I didn't do this ahead of time. I wasn't really thinking. But that's alright. You can see my thought processes. Maybe that'll help. And then it says, assuming a 30-pound equivalent fluid pressure, which I like to look at this as 30, I guess you could do KCF or KSF, let me think. I think it's KCF. I might have to go back and change this later or correct myself, but that's alright. I'm going to go ahead and roll with it. But it says that you have, actually let me just take this out here. So this is the way you want to look at it. And we're just looking at the stem, and it says assuming a 30 equivalent fluid pressure, what is the magnitude of earth pressure at the base? The total, so we're looking for the magnitude of earth pressure, the total earth pressure, and the bending moment at the base caused by the earth pressure. Alright, and here we go. So first to find what this earth behind, so this is earth. I guess that's the best way to show it. Sometimes what we'll do is we show it like that. 1, 2, 3, or sometimes you show it like that. And there's your, just to show it's ground, and maybe backfill or whatnot. But this is how soil pressure works. Typically what you'll do is you have, I said KCF, that can't be right. That's a heck of a lot. It's got to be PCF, 30 pound, yeah. This is PCF. But anyways, a lot of times you'll look at a soil and it'll weigh 120 pounds per cubic foot, or you just 120.12 KCF, and that's kips. I hope we know that by now. So that's the weight of the soil, and I guess I don't think they go over this that much, but all you need to know, I'm going to try to do this real quick and not very technical, is the soil, it'll fail on certain planes and degrees, and because it's not like water. Water will directly, it will push out, you know, because if you let water go, it'll go. So the water is actively being held in by that wall. And since the soil, if you took away, let's say you had a wall like this, you know, a foot high. It's only a foot high. If you took away this wall, that soil might just stick there, because it's not a, you know, if it's very sandy, well, it might start to slough off, and it might fail on you. But in the end, it's not like water. So instead of getting 120 KCF, you actually get 30 or 0.3 or 30 PCF of equivalent fluid pressure is how they like to look at it. So you get an equivalent fluid pressure, and then that's going to, the deeper you get, the more it's going to be, and I hope that makes sense. So it will make a pressure wedge like this. And so you take this and you first multiply it by how deep you are, so you're 12 foot. So you say 30 PCF times 12 foot equals, and it's, in my opinion, is really important to carry your units in this, because it gets awful confusing, at least for me, if you don't carry your units, because I found that not all textbooks and not all guides actually call these things the same thing. Some of them will say call this P, some of it will call it something else. We'll call it P for right now, since I already said that. But a lot of people, they name it different things, so it gets a little bit confusing. So let's say 30 times 12 equals 360. So this is actually 360 PSF, pounds per square foot. Alright, so you now have that wedge. Now you need to think, this is actually a three-dimensional wall, of course, so we're just going to measure it for every foot of wall section. For every foot of wall section is how we're going to look at this. So that kind of takes another foot out of this. But anyways, now you want to figure out what's the area of this. And it's just like you're looking at a beam. You want to take the area under that curve, and it's an equivalent pressure, and it's going to be 1/2 the area. Well, not 1/2 that area. It's going to be that area, but that's 1/2 the base times height, and then it's going to be at 2/3. So this is 12. So 12. This is 12 foot divided by 3 equals 4 foot, and then we have what, 12 foot and then 360. So we have another 12 foot. Oh, 1/2 in front of that because it's a triangle. 1/2. This is 12 foot. This is 360. PSF. And then equals 0.5 times 12 times 360 is 2,160 pounds per linear foot. So if you look at it if you kind of took it where the wall was that way, this would actually be a line load. But we're going to say, okay, so if you have 1 foot width, you can go ahead and the math would be just multiply this by 1 foot times 1 foot is 2,160 pounds. So that makes sense. So now you're looking over here and you see pounds. Oh, okay, that makes sense. But this is actually pounds, and I like to sometimes put per foot of wall. And I hope that makes sense, what I'm trying to say here. And that's when you're looking at capacity, you can now do it per foot. So your B, when you're looking at the wall right here, and you're looking at this section right here, your B can now be 12. Because you're actually going to cut it. Where it's going to be the worst is right here. That's going to be your worst moment. So you're actually going to cut this, and it's going to look like, kind of like, let's say it looks like this. And this is what I meant by you're taking a 12-inch section. So you're going to figure out what the reinforcing is per every 12 inches, and you're going to solve that way, as opposed to saying, hey, this is a 600-foot wall, so my B is 600 times 12, which gets pretty large, and you have to count all these different reinforcing bars. It just gets a little messy. So this is typically how you will do reinforcing bars like this and slabs and whatnot, and you just do it per foot. So it's 2,160 pounds per foot of wall. And now we can go ahead and get the moment. Actually, let's see what they were asking again. They said, what is the magnitude of earth pressure at the base? I would say the magnitude of earth pressure is 360 psf. The total earth pressure, I would say, is P, which is 2,160. Let's make sure that that's what they're saying. It says soil pressure diagram is triangle varying at the height. It says 360 pounds per foot. Of course, I said 360 pounds per square foot, which you might want to go through that and understand what I'm trying to say is compared to what they're saying. And then they said we're getting the same numbers. Yeah, 2,160 pounds, and I said pounds per foot of wall. You can come over here and say 360 pounds per foot of wall, if that makes more sense to you. I hope you understand what I'm saying right there, because if you say pounds per foot of wall, you're actually doing pounds per square foot. Alright, so we have the exact same thing that they do. I don't want to confuse you that they were different. They are the same. There's one of our answers, and here's the other one of our answers in the terms they like to see it in the units. Alright, now we're going to go to the bending moment, and this is pretty easy. You just say 2,160 times the moment arm, which M equals 2,160 pounds. per, sorry, that's kind of messy, per foot of wall. I'm just going to say per foot. I'm not going to put per foot of wall. And then I'm going to say 4 foot. So that's 2160 times 4 equals 8,640. And that's going to be in foot kips per foot. And let's make sure that's right. Yep, 8,640 foot-pounds. I said foot kips. Obviously, I wasn't paying attention. It is foot-pounds. LBS. I am so used to using kips that I just threw it on there. Alright, 8,600 foot-pounds, sorry, said it again. And that is your last answer. That's your moment, and you would design your steel for this, and it would go up your entire way. And you would want to make, you have to develop the steel down here as well. And sometimes, just here's something that you might use in real life is having this steel hang, because most likely what they're going to do is they're going to come in and they're going to pour this the foundation, or this foot, this toe and the heel first. They'll have a construction joint here. Usually they'll key it. I guess they don't have to, but they'll have a key to help with shear here, and then they'll have this sticking out. So this will be cast and dry, curing, and then they'll come back and do this later. But having that reinforcing sticking out 12 foot might be a little long, so sometimes they'll have a bar like this that's sticking out. They'll have the bars like this, and then they'll lap it. So they don't have to have this bar sticking up 12 foot and have it mess around. It kind of depends how you want to do things, and just engineering knowledge, and talk to contractors, see what they like to do, and you'll get a feel for what they like to do. Alright, I hope that helps, and I will see you on the next problem.